So in this video we're going to talk about we're going to introduce the tool called the shear diagram and the tool called the moment diagram. Alright, so the reason we're interested in determining or drawing shear diagrams and moment diagrams is that the location of the maximum shear force, alright, and the location of the maximum moment within a structure. Alright, so at these locations are the most likely failure points within a rigid body. Alright, so our goal is to determine the shear force as a function of x, or x is like the length of the beam. Alright, and then our moment, alright, and we also want to determine the moment of x. Alright, so the moment is a function of the length of the beam. Alright, so how we can determine m of x, v of x and m of x is we can look at the next page for a set of instructions. Okay, so if we go to the next page here, alright, the first thing we're going to do is we're going to find our supporting reactions. So in order to find the supporting reactions, we use the equilibrium equations. So we'll find the reaction forces and moments at the support. Alright, so forces will be either parallel, along, or normal to the beam, or they're going to be perpendicular to the length of the beam, or the beam shear. Alright, so once we have our supporting reactions, we can determine moment function, the moment shear and moment functions as a function of x. So to do that, what you will do is you will draw section cuts along the beam in different sections. So the sections basically will occur before and after applied loads and distributed loads, and before and after reaction forces. So like to the left of where the force is applied, and to the right of where the force is being applied. And then we will use equilibrium equations to calculate v of x and m of x for each section. Alright, and once you have v of x and m of x for each section, what you can then do is you will then draw the shear moment diagrams. Alright, so you plot. So you have the equations that you determined in step 2. So you plot v of x, and then using those equations, and then you do the same thing for m of x. Alright, and typically you will draw both of these plots underneath the free body diagram of the beam. Alright, so to show an example of this process, we're going to go back to the last page, and we're going to go through how we can determine the shear diagram and the moment diagram for the beam. Alright, so step 1. Alright, here. Alright, is we need to find the support reactions. Alright, so in this case we have a roller at point C, so we would have a normal force at point C. At point O we have a pin, so we would have O of x and we would have O of y. Okay, so to find the supporting reactions, we would, if we summed all the forces in the x direction and set them equal to 0, we could solve for OX. Alright, if we sum the moments about point O and set that equal to 0, we'd be able to solve for the normal force at point C. And if we summed all, after that, if we summed all the forces in the y direction and set that equal to 0, we'd be able to solve for a y. Okay, so these are now known values. All right, everything else in the diagram that's on the left-hand side of the video here are known values. So A is known, the length A is known, the length B is known, the total length of the beam is known, the force P is known, and the distributed load is known. Okay, so we know all the applied forces in our system. Okay, because we know all the applied forces, we should be able to determine the reaction forces. All right. So, all right, the second step of our problem is to take the section cut take section cuts through different sections of our beam. All right, so these will be occur before and after applied loads. Okay. So in this case, we're going to draw 3 section cuts. One, our first section cut would be through a section part of the beam where the distributed load is being applied. Our second section cut would go in between where our distributed load is being applied and where our point load is being applied. And then our third section cut occurs after where that point load is being applied up until the roller joint at point C. So what we can do now here is at 1, alright, if we draw our section cut, alright, what we'll have here is we have our distributed load W, alright, applied to the section. On the left hand side of the section we have point O, alright, and then at we'll have O of Y. There's no O of X in this situation because there's no applied forces along the X direction, so we're not going to draw OX. And then we have the length of this section is variable, so we'll leave it as a variable. We'll call that variable x1. Alright, and then we'll include our 2 internal forces. Okay, we'll have our shear force. Alright, I'll call this V of x1. Alright, and then we'll have our moment, M of x1. Alright, so once we draw our free body diagram, alright, what we're going to then do is we're going to determine our 2 unknowns, M of x1 and V of x1, using the equilibrium equation. So to find V of x1, so what we're going to do here is we're going to sum all of our forces in the y direction and set that equal to 0. And if we get if we do that, we'll get O of y minus V of x1 minus W times x1. Alright, so if we solve for V of x1, it's going to be equal to OY, which is a constant number, minus W x1. Alright, so we can follow the same process for the moment. Alright, so we take the moment about the right hand side, so at x is equal to x1. What we'll end up getting is we'll get minus O of y times x1 plus w times x1 times x1 over 2, where x1 over 2 is the centroid of our distributed load, and then we get plus m of x1. So if we rearrange and solve for m of x1, we'd end up getting O of y x of 1 minus w over 2 x1 squared. Okay. So if we redo this, alright, so now we have it within, so we have it for, from, this is, I guess these two functions are true. x1 occurs between when x is 0 and x is equal to a. Okay, so what we're going to do now is we're going to find out, we're going to solve for the shear and moment functions when x in the x2 region, which is between point A and point B on our diagram here. All right. So we're going to draw a free body diagram again. All right, and so what we'll have in this case is we'll have our distributed load W, alright, for a distance of A. Alright, we will have our applied load, or our reaction force OY still, and then we will have our section cut will occur, so we'll have V of x2 and we'll have M of x2. Alright, so those are the loading situations in this case. So if we get that, so what we need to do now is we need to solve for M of x2 and V of x2. So we're going to just follow the same procedure. We're just going to sum all of our forces in the y direction. Alright, set that equal to 0. Alright, to find v of x2. So if we do that, we'll get O of y minus W times A. Alright, plus or minus V of x2. Alright, so V of x2 would be equal to O of y minus WA. Alright, and then we can do the same thing. Or we can just find M of x2. We can sum all the moments about the section cut. Alright, so if we do that, set that equal to 0, what we'll end up getting is we'll have minus O of y times x2 plus W times A times x2 minus A over 2. Alright, and then plus m of x2. All right. So m of x2 is equal to is going to be equal to O of y minus or times x2 minus WA x2 plus W A squared over 2. Alright, so that's our second section. Alright, and then our last section cut number 3. Alright, what we'll have here is we'll draw a free body diagram one more time. So we still have our distributed load. W for a length of A. We still have our applied load OY. Alright, and then at a distance B, we have our applied load P. Alright, and then after that applied load, we have our section cut. Alright, so at our section cut, we will have our shear force V of x3, and we will have our moment M of x3. Alright, so again, to find V of x3, we're going to sum all of our forces in the y direction and set them equal to 0. If we do that, what we'll end up getting is we'll get O of y minus W A minus P minus V of x3. Alright, so we'll get V of x3 is going to be equal to OY minus WA minus P. Alright. Alright, and then we'll have sum all of our moments about the end point, or at x3, and set them equal to 0. So if we do that, you will get O of y minus O of y times x3 plus WA times x3 minus A over 2, and then we'll get minus plus P times x3 minus B, and then we'll get then we'll have to add M of x3. Alright, so if we solve for M of x3, what we'll end up getting is we'll get O of y minus times x3 minus WA times x3 minus A over 2 plus or minus P x3 minus B. Okay. So now we have all of our shear functions and moment functions, so we can now draw our shear moment diagrams. Okay, so we're going to go back to our diagram here, and we're going to first draw our shear function. All right. So we're just going to draw a graph here. All right. So our three shear. So we have three regions. We have region 1. So this is where x1 is in play. The functions that we have as a function of x1 are in play. We have x2, which is between point A and point B. All right, and then we have x3, which is everything after the applied load at B. So what we'll end up getting here is we'll have we'll have O of y. Alright, so at x is equal to 0, we have O of y. Alright, so we're using at x is 1, we have v of x1 is equal to oy minus w x1. Alright, so this is O of y is a constant, w x1 is basically a slope of a line. So what we'll get is something that looks like this. Okay. After that point, within x2, if we look at it, we have a v of x2 is equal to O of y minus w times a. O of y is a constant, w is a constant, and a is a constant. Therefore, our shear force from point A to point B would be a constant as well. So we would get from this point to this point, we have a constant value. So this is O of y minus WA. Alright. And then at point B, we transition to the third region, which we know that V of x3 is equal to O of y minus WA minus P. Alright, so all of these are constants as well. Alright, we solve for that down below during our third section cut. Alright, and then at the very end, at point C, we would add our normal force NC. Alright, and then for a shear diagram, the forces should always add up back to 0 at the start at the end of the diagram. Alright, because the sum of all the forces in the y direction across the whole beam have to be equal to 0. Alright, so this would be our shear moment diagram. Alright. So So then the next step would be to draw our moment diagram. So this would be our moment diagram below. Again, we'll have three regions. We'll have our region for x1 that goes between 0 and A. We'll have our region that will be x2, which will go between A and B. Then we'll have our region x3, which will go between B and point C. Our diagram. So we'll end up having our three equations from our three section cuts. So our first section cut, we have O of y times x1 minus w over 2 x1 squared. So that's going to look like a parabola. Alright, so it's going to have something like this. Alright. Alright, and this is the m of x1 function, which is equal to O of yx minus wx squared over 2. Alright. And then from point A to point B, we get our moment function. It's going to be equal to OYX2 minus WAX2 plus WA squared over 2. So if we do look at that, what this ends up being is we get let me look at this again. O of y x2 minus w x2 wa x2 over 2 wa x2, and then plus wa squared over 2. All right. So again, we'll have a all right, so in this case we have only a, so this should not be x squared, it should be sx. Alright, and then so we have in this case just everything to the power of 1, so this would be a straight linear line here. Alright. Alright, so this would be our second part of our shear moment diagram. And then our last thing we have will be the moment x3. So that would be from the last section cut we took. Alright, so this is our equation here. Alright, so we're going to copy it over here. Maybe not. Anyhow, we get O of y times x3 minus wa x3 minus a over 2 minus p times x3 minus b. For our function here. Alright. So that is again going to be, the largest power we have is 1, so it's just going to be a straight line again. Alright, so we're going to just have a straight line down and ending at point C. Alright, so those are our two shear moment diagrams, and that's our shear diagram and our moment diagram. So we were able to calculate the functions from point O to point A, from A to point B, and from point B to point C for both the shear and the moment using section cuts. We were able to solve all for the individual shear and moment functions. All right, so we're going to do one more example of this with numbers instead of all variables, but this is the general procedure you will follow in order to determine your different section cuts with your functions, your shear moment functions within a beam.